Okay, so for this week, I'm continuing on the theme of Python programming for biologists. Hopefully, some of you, most of you have had a look at the Python for Biologists ebook and website, which goes into the exact same stuff I'm going into, but you can take it self-paced and it's a little bit more detailed. Obviously, there's lots and lots more intro Python books. You can follow any of them that you want, because I'm really just trying to get you up to speed so you can use this as a tool for data analysis and visualization throughout the rest of the course. So today we're going to cover a few more fundamental concepts, and I'm going to give you some examples. Flow control is a big one. How do you do loops? How do you set up if questions? For loops. Recursion, reading and writing files, so I/O, input, output of data to your program. That's obviously going to be essential for us. Creating custom functions and dictionaries, which is another data type that's important in Python and we make use of a lot in bioinformatics. Okay, so I'm going to start right off with flow control. Programs need to make decisions and have loops. Repeating operations for a specific number of times. Frequently, you want to nest these things together, so you repeat an operation and then test whether something is true or not, and that'll determine how many times you repeat an operation. We have decision operators in Python, if, else, and else if, which is spelled E-L-I-F. That's just a Python thing. And we have looping operators. The two most common are for loops and while loops. So a for loop iterates, steps through repeatedly a list, one element at a time. And in Python, loops and decisions are set off by a colon and an indent. So I have an example here. For I in my list, colon, indent, then a variable name is equal to that variable name plus something else, another variable. The I is a variable that is sort of created on the fly and is the indexer for the loop. So you're going to go around the loop I number of times. Well, how many elements of I are there? It depends on the list. In this case, the list has 4 elements. So Python automatically loops through this list until there's no more elements. There's a list index, so you could know which number of the list you're currently on. A lot of programs don't count on that. They keep sort of an internal tally of how many times the loop has gone around, creating their own index variable. Yeah? Yes, this syntax is very important. It has to be exactly like this. For I in, and then the in is something. It is frequently a list. It could be something else. But the thing is what Python calls an iterable, a thing that has a number of elements that you can step through over and over again. The simplest iterable here is a list. You'll encounter more sophisticated stuff, but let's build complexity a little bit at a time. Okay, the for syntax is very simple, but the indentation is actually really important. And working with PowerPoint is not the ideal way to show this stuff. Python recommends that you indent 4 spaces. And the one thing is super important is that it has to be consistent. Everywhere in a program, your indent has to be at the same level. Also, what happens very frequently in Python is that you have multiple indent levels. Every time you create a loop, every time you create an if statement, every time you create a function, you have an indent. And then maybe another indent, and then maybe you come back out part way to finish up something in that level of the logic. So not too many other programming languages care so much about white space. Python is really focused on indents, and that's like the second or third most common beginning Python programming error, is messing up the indent level. Okay, so this is like a little code snippet for you to try, and hopefully you get the output of that green thing that I put at the bottom there. If not, then it's time to learn debugging and do it until you get it right, because debugging your work on very simple problems is less frustrating than trying to attack a more complicated problem without having completely nailed down the simple skills of formatting and syntax. So go through this stuff and make sure you've got it. So here's the big red arrow showing the indent. I'm not sure that's 4 spaces. It looks like more, but work with me here. I'm dealing with PowerPoint. Okay. You can also loop through a string. I mentioned last time that Python deals with strings as a form of a list. It's a list of letters. And so you can say for I in my DNA, where my DNA is now a string of letters. And if you tell it to just print I, it'll just go through that string letter by letter around the loop each time and print the letter. You know that it's going through the loop each time because the print statement produces an automatic carriage return. And then you come around the loop another time and you come to a fresh print statement where the value of I is now the next letter, and so it prints out on the next line. So it's pretty clear that you didn't just print the variable my DNA, you actually went around this loop for the number of times that there are letters and printed out each one each time. Yeah? Yeah, I screwed up. It is case sensitive. If I change it here now, am I going to remember to change it on the one that I archived? I will try and remember that. Good catch. It's super hard to copy paste stuff and never make a mistake. Right. It is very case sensitive. Okay, now we're going to talk about making a decision, an if-else type decision. So if obviously splits your flow down 2 paths. The program will do one thing if the if statement is true. It'll do another thing when the if statement is false. So if my DNA find GC, which is a function which will evaluate to true or false. So if find GC is true, after the colon, it'll execute the indented statement. If it's not true, it'll skip over the indented statement. That's the way an if works. It does the thing or it moves on. So you could think of if as if true. And if always evaluates the thing that follows it in a true-false manner. So if true, do the thing that's indented. If not true, skip over the indent and move to the next command. And else is only executed if the if is not true. So if the if is true, it skips over the else. As opposed to just if there's no else, then it'll execute the next command. But an else is only executed if the if is true. Syntax-wise, the else is out here at the same indent level as the if. There's also this idea of else if, which asks another true-false question, and again executes the its indented block only if the second true-false question is true. I mean, anyone who's taken a little computer science is really familiar with this, but I'm talking to the people who've never taken any computer science because we're trying to bring you up onto that page. So the else here will only work if the first if fails. Now, after the else, you could have more commands in your program, and they will be executed.
Have another if under the else?
You can, but it will be a completely separate logic. It will not be related to the result of the first if. If you want to make them contingent, then you have to do an elif. But the else is always last. So you can say if, else if, else if, else if. Else is the last. That catches them all. Is it an A? Is it a G? Is it a T? Is it a C? Else, it's not a coding letter, right? So it catches all the other events, which is a good way to code. It's sort of an error catch. If your data is not 100% perfectly clean, you could put an else in there, and the else could just be, this data is unreadable, and the program prints that, instead of just failing or giving no result, which is a confusing result. If you want to write some code, that's a good way to do it. If you work with code and it gives you that sort of a result, now you have a clue why it happened that way. OK, now we're on to operators. If statements need to have operators so they can evaluate things. I mean, you could, the simple ones, equals, greater than or equal to, less than or equal to, not equal. And then we have your math functions, plus, minus, divide, times, raised to the power. And you can also have complex if statements. You can say, if A is true and B is true, then do this. Or if A is true or B is true, then do this thing. And obviously, those two will give you very different results. And it's a sort of a higher level programming error when you get your logic wrong. And it gives you an unexpected result because, an or rather than an and somewhere in your logic. So an example here, and again, I'm hoping that you guys will work through these examples either while I'm talking or tonight when you go over the slides. So we have a DNA string. We're counting G's and A's. And we're saying for the base in DNA, OK, DNA is now this string, and we're going to loop through one base at a time, just like I showed before. So if the base is equal to G, then the count of G is plus equal 1. So I'm incrementing. So count G is now count G plus 1. Important programming skill is that if you want to keep a tally of things, a running count, you have to initiate that count outside of the loop. If you initiate the count in here after the for, it'll get reset to 0 every time you go around the loop. And so you'll end up with either 0 or 1 as your count rather than a proper count. So in general, variables that you want to use inside the loop, if you want to move that information out and not have it reset every time you go around the loop, you want to create those variables out here. This is sort of like a scoping thing, which is more of a high-level computer science concept. But it's important to have the counter initiated out here. Add 1 to the counter every time you go around. So if the base is G, add 1 to G, elif, add 1 to A. And I didn't put an else in here because I'm only counting the number of G's and A's. And I'm just assuming that every other character in the string is not a G or an A, and I'm not going to worry about it. So I'm not actually printing a GC percentage, which would kind of assume that I ought to keep track of all the other letters, or at least the length of the string, maybe keep a tally of improper letters, that sort of stuff. So yeah.
Do you have to use the else if there for the A, or can you do if base G and then also do if base A? Will it still work?
I think it will still work.
The difference is just if you put another if there, it's inefficient because it will always consider the next if. Whereas if you put an elif there, if you count for G, it will just go through the next loop. Otherwise, if you put just an if there, it will again, even though it already counted a G, it will again check if that G is an A.
True.
So that's why you use an elif and not if.
Also, the logic works a little better. If this was going to become a more complex statement where I was going to count ends and underscores and gaps and that sort of thing, I can add more easily to it in this structure than having a whole bunch of separate sort of unrelated if questions that I'm asking of each data item. It's better to say, which of these categories does this piece of data fall into, rather than, yeah. So structurally, it's better. And as he said, in terms of efficiency and memory management, it's better. And it'll run faster, too. But I didn't think of that. So all good. OK. Functions. We're actually cruising really quick here, so this is good. More complex operators are known as functions. And you've already actually seen some functions that I've thrown at you, things like length or whatever, count. Functions can do anything you want. Functions are actually small programs that are embedded inside of other programs, or they can be separate pieces of code that you import and then use inside of your programs. So they could be standalone, or they could be part of your code. In other programming languages, we might call them subroutines. Functions use parentheses to act on a data object. It always uses this syntax. So the function name, parentheses, and then some object inside the parentheses, which is the target of that function. Generally, it's a variable or a few variables. Now, functions can take more than one input, and those are separated by commas. And you don't necessarily know in advance, all the possibilities. But if you're writing the function, you can require as many input parameters as you want. If you're going to compare, if your function is going to compare two strings, then obviously you would want to input x and y, where x and y are strings. And you might even want to test at the first step in your function, do x and y actually contain strings, or else my function is going to fail miserably. So open is a function, read is a function, append is a function, write is a function, length is a function. Oh, well, I'm out of slides out of order. I'll get back to that in a second. Well, range is a function. Range creates a list of integers. So if you wanted to input some data, rather than typing it all out and saying, my list equals, brackets, and then start typing out 1, 2, 3, 4, that's dumb. You could just say start, stop. So you could say, range 10. And it'll give you the integers from 0 to 10. Here, again, actually, it gives you the integers from 0 to 9, because that's the way Python counts. It counts starting at 0 and up to, but not including the last element of your range. That's just the way it always works. Sometimes it works out very intuitively. Other times it gives you an off by 1 error, and you have to go back and debug your code, constantly watching out for that pesky 1 before the end of the range kind of thing. But what does work nicely, I show it right here. So range 10 gives you from 0 to 9. Range 4 to 11, step by 2. So step is one of those things that's an optional parameter. So the range function can take either 2 or 3 input parameters. If you give it 2, it assumes it's a start and a stop. If you give it 3, it assumes start, stop, and step, number of, increment size, step size. So if you say range 4, 11, 2, it counts from 4 up to, but not including 11, stepping by 2. So you get 4, 6, 8, 10. Test this stuff yourself in case I've got more typos in here. It happens. So range works nicely inside of, or as part of, a for loop. I use this construct pretty often, and you'll see it in other people's code, so it's not just me making this up. It's used as a part of a for loop to step through a list while you keep track of what number item in that list you're working on. So you have a list. In this case, it's a list of strings. And we say for I in range length A. So that means going through list A from the 0th item to actually the last item, because range len works that way. Both the list is indexed and the way you calculate the range work together to give you all the items in the list, and also tell you which item you're working on. So I in range length A, well, I is the 0th item, and then it's the first item, the second, third, fourth, etc. So I'm printing I, which is the index, and A of I, which is the ith element in list A. This guy understands. The rest of you, yeah? Okay. So this is handy. It looks silly, but it's handy. You'll use it soon. Yeah.
It's kind of confusing because you didn't use parentheses for print. I thought for every function you have to put parentheses.
It does have parentheses. Range has a parenthesis around it right here.
But print doesn't.
Oh, print doesn't, yeah. I'm still functioning with the Python2 versus Python3 dichotomy. So yeah, this will work just as well, probably a little better. It'll be a little bit future-proof if I give print a parenthesis. It used to be that print was like a special feature of this code and not considered a function, and now it's considered a function. So
But it works without parentheses.
it works either way. If you're running a version 2 Python, it will give you a syntax error if you're running a version 3 Python, because it'll say print statement not, function not correctly parameterized or something like that. So yeah, I haven't updated all of my thinking, let alone all of my slides to be Python 3. And it may be a little while because Python 3 has been around for a couple, 3-4 years now, and people are converting slowly because it creates as many problems as it solves. So yeah, and yeah, so now print is a function, and so it requires its own brackets. Parentheses. Brackets are square things. Parentheses. Okay. Yeah.
I just tested there's a little difference between for the parentheses in Python 3. So for example, if there's only one output, if you want to print I, there's no difference for the parentheses. You can add it or doesn't add it, it doesn't matter. But you have two outputs, there will be different. So if you say print parentheses 1, 2, it will print parentheses 1, 2. If you just print 1, 2, it will only contain 1 and 2. There's no parentheses. So you can try. There's a little bit difference.
Okay. All right. A list compression is a higher level concept, and it's not essential for you in code, but it does allow you to write more efficient code. The reason I have to show it is because part of this basic Python skills is being able to read other people's code, and experienced coders would always do this because it saves time, and for them it creates better clarity. So you can basically embed a for loop inside of an if statement. So instead of saying for x in range 10, if x to the second power is less than 50, append to this list squares that value, and then print them out. Instead, you could say this list equals x squared for x in range 10 if x is less than 50. So the logic is the same, but like it says, it compresses it down into one nice, neat statement and dumps the value of that expression into the list all in one shot. There are zillions of ways to use list compressions to do, fairly complex amount of work all in one line. So it's also a nod to like Perl programmers and Java programmers who love to do a lot of complicated stuff all in one line. But I just wanted to show it to you. A fair number of the concepts I'm trotting out here are for you to understand that they exist, and you can use them in your work or not. If you know the basics, like a for loop and an if statement, you can get by just doing it the clunkier way, which may be clearer for you in your code, and I'm okay with that. If you want to sort of progress and get more sophisticated, then you learn how to write list compressions. All right, so I've trotted out a bunch of functions. The main reason I've done that explicitly is so that now I can teach you how to write your own functions, which act like subroutines, I said before. Or you can use the functions written in code by others, which are mostly available as Python modules, some of which are already built into the Python that you've downloaded. If you've downloaded Anaconda, you've actually got dozens, maybe even hundreds of modules preloaded into the Python code that's sitting on your computer. But they're all dormant. They're waiting for you to launch them as you need them. That's important because if you launch them all at once, many of them contain the same statements and they would conflict with each other. Plus, they would use up a lot of active memory in your computer. So you don't want to have every single piece of Python code active at once. It's designed to be modular. All right, so the function code in Python where you define your own function is simply def. And again, it uses this name, parameters, colon syntax. And then the function itself is all indented from the def statement. So another thing about defining a function in Python is very frequently the function is something that's a utility that you're going to use later. So the function itself probably doesn't contain or directly access any data. It takes the data as an input. So first you define the function, then you define a piece of data, and then you run your function on that data in order to test whether the function is working. If it works nicely, then you have that function available. Hopefully you save that block of code in your library of Python scripts so you have it available to you, whenever you're going to need it in future. Or you may use that function multiple times in one script, always just calling it by name after you've defined it. Okay, so I'm going back to this idea of counting G in a DNA, and I'm assuming now that DNA is a variable that contains a string, which presumably has DNA letters as the contents of that string. All right. In this case, I'm setting a count variable to 0 before I create a loop. Now I'm creating a loop for base in DNA, again assuming DNA is a string. If the base is equal to G, I'm incrementing my count of G and I'm returning the count. Return is another really key function, another key aspect of a function. Return is the output. So you define what the function takes in and what the function outputs. So conceptually, it's just like a function in math, right? It has an input and an output, and what goes on inside is a little bit of a black box, but now you're the engineer of that black box. So it can do whatever you want and output. One of the interesting things about a function is it's not limited for data types, right? It can take in a string and output an integer or a real number or a complex print statement that is formatted any way you want. So a function can be a relatively sophisticated program, but it's probably smarter to make a function relatively narrow and targeted. Although this might be a little too narrow. I mean, you could create a function that counts all 4 bases or calculates GC or calculates whatever you want for a given input and output. The only thing about a function that's required is that it has a well-defined input and a well-defined output. Okay, so here's an example, trivial again, but something for you to try. So this is my find ATG function. Again, it takes as input some string of DNA. So I'm defining a find ATG with a colon. I'm starting right in with the if. If DNA.find, that's another function that is already built into Python that I'm using inside of this function. If DNA.find ATG, return ATG is found. Really, really, really stupid. It doesn't really do anything that DNA find your string name wouldn't do, but I'm trying to make it simple. Else return no ATG found. So point here, one function can have different return values. but you have to distinguish between them. You can't return and then keep returning and keep returning. Once you return, function is over. So if and multiple returns work nicely because if is either true or false. And it creates a branch point. And you need to end both of those branch points somehow. So if you create a branch point that ends in a return, you don't have to worry about the function going on. The code is over, and now you return to whatever code called that function. So the function has done its job and returned a value back to you. Yeah?
So what's the difference between return and print here?
Big difference. Print puts something on the screen only. If you're using a function inside of other code, printing to the screen may be completely irrelevant because the rest of your code may be writing an output file. Whereas return takes that value and brings it back to the rest of your code where the function was called. So I'm trying to show you how this is working here. So I've defined a function, right? Find ATG. Now I'm moving on. These little greater than symbols suggest that I'm now interactively working with Python, or I'm further down in my script, and I've defined at this moment, I have a variable, my DNA, which now contains this particular string. And now I call my function. I say, find ATG in my DNA. OK, and it says ATG is found. Well, that's cool because what I could do is if my DNA, say, skipped through an entire file that had lots of stuff in it, a bunch of sequences, and I was looking for something perhaps slightly less trivial than ATG, or maybe I'm just really keen on finding ATG in a lot of sequences. So I could iterate my DNA or as a counter that skip through many sequences. And for each one of them, I call find ATG, and then it returns a value, and I could write that value into an output file somewhere. It's not absolutely required that I do it interactively and put the result on the screen. Because it's a return value, I could assign that return value to a variable. I could write it into a list. I could do whatever I want with it. Whereas a print, you don't have any other options. All it does is print it on the screen. So, excellent question. This code has bugs. Most of my code does. There are situations where the data will break the code. So if you find an instance where the data, some sort of data will break this example, and you fix the code so that that doesn't happen, get a bonus point, like worth an extra homework. I have at least 2 more in here that, I could see the bug, but fixing the bug would make the code much less clean and the example require a lot more explanation. So I know I can see the bug. OK, yeah?
Excuse me. I was testing a sequence without ATG, but it's giving me an output saying that I have it.
You have it. So that's a bug, isn't it? It shouldn't, I don't think. I'll have to try it again. I thought I had this working, but it definitely has a bug. It worked for you? So maybe it's a syntax error. Yeah, mine worked. So, the kind of bug I'm thinking about is not so trivial. It's like if you give it some slightly different input, then you may have troubles. What if there's a carriage return, et cetera, et cetera? Or what if there's a space in your input data? OK. Recursion, major topic. Now we're stepping off the diving board into the world of algorithms. And I'm going to have a little aside here in a moment, talk about that. So now that you know how to make a custom function, what would happen if you made a custom function that called itself? So, and I copied this one from the Think Python book, just in case you're wondering. And hopefully I copied it without typos. So they have this nice little blast-off countdown function. and give it any number. So n in this case has to be an integer. So you would say countdown 6 or countdown 3. And if n is less than 0, it prints blast off. Less than or equal to 0. So if n is counted down to 0, it'll blast off, right? Else, it'll print n, and then it'll call countdown again on n less than 1. So how would that work? So if you give it countdown 2, is n less than or equal to 0? No. So it'll print 2, and then it'll call countdown of 1 minus 2, so it'll say countdown of 1. Now n is 1. If n is less than or equal to 0, it's not, so it'll print 1. And then it'll call countdown of 1 minus 1, or 0, and it'll say, is n less than or equal to 0? Yes. So it'll print blast off. So give it a try. Should work for you. I liked it a lot. Yeah?
Is there any way to make it like delay for
Yeah, there's delays. I don't know what they are, but it's in there. Wait, and I think that the default is by seconds. So like wait 6, but Python is really well documented, and there are many, many, many internet forums. So you can basically just ask Google your question, Python program wait, and it'll give you a decent answer. Or use ThinkPython and just look it up. I also, O'Reilly probably puts little snippets of some of their other books, Python in a nutshell. So documentation is easy. I don't have it all memorized. Pam has it all memorized. You can ask Pam, but it's easier to ask the internet, because first, you should ask the internet is the answer that everybody will tell you. Okay, if you can do recursion, then it's really easy to create an infinite loop. Don't do that. On your own computer, there are some safety features installed so that after some amount of infinite looping, it will eventually give you an error, but it will infinite loop for a while. So why is this an infinite loop? Give it a try, but be ready on the command stop feature, or get ready to kill it, because it's going to run forever. Why does it run forever? Okay, +2 of n prints n, and then it adds 2 and calls itself again. And it prints n +2, and it adds 2 more and calls itself again, et cetera, et cetera, et cetera. So it's a nicely nested infinite recursion. Don't do that. So when you're writing a program that calls itself, be sure that it's going to converge. It's going to terminate at some point. So counting down and making it stop when it hits 0 is a valid way of doing such a thing. There are obviously lots of others. All right, here's your first coding challenge for the day. Up till now, I just gave you coding things to test on your own. I'm not giving you the code for this. I resisted, even though I enjoyed writing this last night a lot. This particular piece of code I managed in 7 lines. And the Rosalind people, all right, digression 1. Rosalind has several more sections. I gave you the baby steps, the Python village. That's really like the kiddie pool. The Rosalind creators are algorithm people. They actually use Rosalind to teach a computer science course in algorithms, as well as a course in computational biology and a 3rd course in bioinformatics. There are 3 different textbooks that all use Rosalind as their problem sets. So go to Rosalind and explore some more of the space there. It will give you endless hours of fun. And it will get you thinking algorithmically, and it will teach you in a problem-oriented way. I'm pointing you to the first problem in the algorithmic section called Fibonacci. And All right, Fibonacci, you probably have heard of Fibonacci. It's one of the most famous mathematical concepts, sort of like prime numbers in terms of an obsession of mathematicians. So the Fibonacci series goes like this: 0, 1, 1, 2, 3, 5, 8, etc. It's defined by this little function here, which is actually an if-else function, but written the way mathematicians write rather than the way computer scientists write. So if your input is 0, Fibonacci gives you 0. So Fibonacci of 0 is 0. So you can think of this as a list, and it's a Python type list because the 0th element is 0, and Fibonacci of 1 is 1. Interestingly, Fibonacci of 2 is also 1. Fibonacci of 3 is 2. Fibonacci of 1, 2, 3, 4. No, Fibonacci of 4 is 2. Yeah, no, 0, 1, 2, 3, Fibonacci of 4. But then it grows bigger, and it starts to grow bigger very quickly. How does Fibonacci work? All right, it's defined here. Fibonacci of a number is the sum of Fibonacci minus 1 and Fibonacci minus 2 of that number. So it's defined recursively. It's the two previous numbers in the index added together to give you the next one. And it grows that way. You just keep adding the two previous numbers. It grows almost as fast as exponentiation. It's really quite impressive. When you get up to Fibonacci of 20, it's a big number. So your assignment, this is a do, not an ABC assignment, a do or don't do or get help assignment, is to write your own Fibonacci program as a function so that you can give it any number and it will give you the Fibonacci of that number. All right, here's a little help. The Fibonacci numbers here, def fib. So this is my fib function. If x is 0, return 0. So fib of x when x is 0 returns 0. If x is 1, fib of 1 returns 1. Else, so if x is not 0 or 1, else if x is greater than 1, return fib of x minus 1 plus fib of x minus 2, right? A perfect example of recursion. Now, what's really interesting is in Rosalind, the developers have given you a little dissertation about why writing the program in this seemingly logical way that follows directly from the definition is a super bad idea. And the problem with it is it counts down from whatever number you give it, right? So if you give it fib of 20, then it has to calculate fib of 19 and fib of 18. And when it calculates fib of 19, it also calculates fib of 18 and 17. And it calculates fib of 18 and 17 and 16. And so every sub-recursion creates 2 more recursions and 2 more and 2 more. And so the number of recursions grows exponentially for every step down that you take. And it turns out to take a really huge number of operations computationally. And it stores all those temporary results in memory. So the way computers are structured are very poor for creating a lot of open loops like this that have to all be stored and then filled back in recursively. So be cautious with using recursion and try and think of a better way of solving this problem. Hint, use a list. I say this as a good introduction to the idea of computational complexity. We'll only touch on this a few times in the course, a lot more if you stick with me in the second half of the fall semester in the, now we're calling it Damn, we renamed the course this afternoon. Fundamentals, we called it Fundamentals of Bioinformatics. Same time slot after the end of October, running till December. 8 more weeks where I get to talk just about bioinformatics and not Python and data and statistics and all the other things that we're covering here. But since we deal with big data and some complex computational ideas, the speed of computing for a given problem can be very important. And sometimes you could solve the same problem in several ways, one of which may be vastly more efficient than another. And sometimes it's the number of operations, like this recursion problem. Other times it's about how many times do you pass through the data, and how much of the data do you have to hold in memory at any one moment. That can vastly influence the speed of execution of a program. Sometimes it turns out to be advantageous to hold a few tens of gigabytes of data in memory because memory is cheaper than CPU for this given operation. So there's not like absolute hard and fast rules. You have to very carefully structure your problem in your mind, and in some cases it's empirical. You have to give it a try and see how well that program executes. And if it's unacceptable, then you have to figure out a different way to do it. So, second digression. Now we get back to one of the main topics, which is file I/O, input, output of data in your program. Up till now, I've created variables and input data into our example programs right inside of the code. But clearly that's an inefficient thing to do, and if you want to process large data, clearly you're not going to be typing and copy-pasting the data into your code. You want to write a piece of code one time and give that code the power to read data files that you tell it to read and do its thing. And very frequently, you'll want that program to write its output into another file, not dump the output on the screen. And so here's where writing a script is much more reasonable than working with Python interactively. So with the Anaconda environment, you're sort of constantly writing a script rather than just typing Python to the greater than symbol and working interactively. You're saving your code. You can reuse that code. So if that code knows how to find a file, read that file, process that file, write its output to another file, then really all you need to do is call your code, give it a file name to input, and give it a file name to output. And it should be able to do the rest. And that's typically the way you'll get commercial software or public open source software. Typically, you call the name of the program, you tell it what data file you want, and you give it an output file name, and it's good to go. So I'm going to teach you how to do that. So when your program just outputs, it outputs to what's called standard output, which in most of the time will be on the screen. So when you call a function and it has a return value, if you've called that function interactively, it'll return the value to the screen. If you want to read a piece of data, you have to point to that data and then read it in. In Python, a file must be opened before reading or writing that file. The open file is assigned to a variable, which the Python programming team likes to call a handle, or they sometimes call it a file handle. It's still just a variable name that is used as a pointer to the file. But there are some special rules about a file handle, which is why it deserves a special name. Very frequently, a file handle gets used up. So when you've created a file handle that points to a file, and then you've read data from that file, you can't go back and read it again. In many circumstances, it's been used up. So that's a rule of a file handle. So the .read method is a simple method to read all of a file into a variable. Captures the whole content of the file in a string. So this assumes that your file contains text, which is probably a good assumption. It's very hard to work with a file that contains something that's not text. Could be an image, could be something else, but then you wouldn't be using the read method. After you're done with the file, after you've read it, you need to call the close method. It does not automatically close itself up. It's just good housekeeping rule. But it'll be problematic if you don't do that. OK, example. We have on our computer somewhere a file called humanpep.fasta. We open that file, and we assign it to this handle called file1. Now we read the file, and we assign the contents of that file to a new variable called humpep. So we had to go through 2 steps and create 2 different variables to get our hands on the contents of that file. The first variable points to the file on some location in some folder on our computer. The second variable contains the contents of that file that's captured with the read command. OK, now we want to do something. We're going to use the count method. We're going to count greater than symbols in the humpep string, and that goes into our gene count variable, which we might use later on for something. And then we close file1. This is another method. OK, so this is really just a framework for you to think about reading data from a file. You always have to go through all of these steps. I mean, the gene count is standing in for whatever you want to do with the contents of that file. In fact, once it's in humpep variable, you've got it, and you can do whatever you want with it elsewhere in your program. OK. Again, this is a little more sophisticated. You don't have to do it this way, but it's nice. It's sort of like the file compression. It mushes a bunch of steps into one, and it takes care of the close for you. You don't have to close if you use with open. So you say with open humpep fasta as file1. This requires the ... indent. With is essentially a loop, but it's a loop that runs one time. So with this as file1, so this is the assignment here to a file handle is being done by the as rather than by the open command here. So with as takes care of open. Well, here's the open. So the as is really just taking care of the assignment. And then you do the read just exactly the same as you did the read here. File1.read, file1.read. So these two are the same. And now you've dumped the contents here. Now the next line of code, you would come out of that indent because you finished that, that little mini loop, which was reading the data loop. And now you've got humpep as a variable that contains the contents of what was in this file on your hard drive. Now it's a variable that contains the contents of that file as one single string, including carriage returns and everything else that was in this original file. OK, if I taught you how to read a file, I have to also teach you how to write a file. Now you're going to be creating a new file on your hard drive that has contents that you specify. To create an output file, again, you use the open command. But now we have to give the open command an extra parameter. We have to give it the "w" parameter, which means open that file for writing. In fact, the default value for open is read. And you could have said open file name, comma, r for read. But I skipped that because if you don't give it a parameter, read or write, it assumes read. So that's a case, another optional parameter that has a default value. Just like step has a default value of 1 if you don't specify a step in a range. So now we're going to use the write method instead of the read method. What we're going to do is, write is actually very similar to print. So instead, when you have a result inside of a variable, instead of printing that variable to the screen, now you're going to write the contents of that variable into your output file. So we're opening as output a new file. And here, inside of the quotes, you make up your own new file name. If you put here a file name that already exists, that file gets destroyed and overwritten with a new empty file that was ready to receive the contents later in your program. So even if your program doesn't do anything, as soon as you open a file with this name, any other file with that name is destroyed. So that's something to think about if you're putting a write command inside of a script that you're going to use frequently. You might not want to always use the same file name. You might want to actually define this file name with some sort of a variable or some sort of input parameter so that it writes out a different file name for each different data that it reads in, or each different time that you run it. You could even ask it for input from the command line for the name of your output file. Just something to think about. So you open a file, you specify a file name in quotes, comma, W. The W also needs to be in quotes. That seems a little clumsy to me, but that's the way it works. Python is not a perfect language. Now, we have this file handle, right? This variable output, which was just created in the previous line. And now we're using that with this write method. So output write means write into the file output. What's the file output? Well, we defined it as having this name. So this output thing, it's a handle, right? It's a variable. It's not an actual file. It's a pointer to a file. We're following that pointer and writing into this text file, which is sitting somewhere on our hard drive. Actually, since we didn't specify where, it's going to be in the current Active Directory where Python is running. So we're writing, this is in quotes, so it's just going to write that as literal text. And then we're going to take the contents of the gene count, which might be an integer. In case it is an integer, we're transforming it into a string so that the print command or the write command, which works very much like the print command, can work with it. And this concatenate operator only works nicely when you're concatenating two strings. Also, I left a little space right here so that the concatenate would look nice. So this is a string, and this is a string, and they write an output into my output file. And now I'm closing my output file. So this little coda, right? This is like the output part of some larger program that's counting genes, presumably back here or somewhere else. And it's now closing that output file. Perfectly clear to everyone? Awesome. OK, another way to work with I/O is to read a file one line at a time. Quite a few programs do this, but I was actually hard-pressed to think of a time when it's greatly superior to read a file one line at a time as opposed to reading the whole thing in and then parsing it later. But if your input file was extremely large, like a few gigs of text, it might be necessary to read it a little bit at a time because it might take a really long time to read the whole thing, or it might use too much memory or something like that. So there's this function called readlines. It's plural, read lines. which captures a file as a list of lines rather than all in one big string. Then you could loop over the list of lines. So sometimes you want to separate the entries of your input file into a list according to the carriage returns of your input file. I could see that. Unfortunately, in a FASTA formatted file, then you get one line of header, one line of sequence, next line of header, next line of sequence. So you'd have to write a program that sort of stepped over every other entry in your list, sort of a step 2 type of a thing, to deal first with the headers and then with the sequences. But I could see where that would be handy. My file open humandna.fasta human seq equals my file read lines for line in human seq print length of line. So that's just an example. It'll give you the length of every line in your file. Some of them will be header lines and some of them will be sequence lines. So you'd maybe have to say, well, does the line start with a greater than symbol? If it does, skip it. If it doesn't, then print the length. And now you'd have the length of all the sequences in your FASTA file. Doable. Or you can iterate over the lines directly. Using this construct here. Now line is, oh, no, it's the same thing. My file, open, human DNA file. Right. This is an iterable. That's what I'm saying. My file is an iterable. Even though it's a handle, it has the feature that if you ask it to iterate, it assumes you mean iterate by line. So this will save you reading the whole file into memory in one swoop and might be useful on some situations. And line here, this is not a required word. This is actually just a variable like I or X that's holding the place that steps you through one line at a time. And this will give you the same exact thing as above. It'll show you the length of every line in your file. OK, another completely important concept. This is a new data type. Up till now, I've only actually given you 2 data types. We've had strings and variables, lists, I guess 3 data types, lists, variables, although this is a data type called a dictionary. And it's it's more than a variant on a list. It deserves to hold a separate place in your memory and say a dictionary is a special thing that can hold data. And in other programming languages, we call it a hash. A hash is a 2-column list where for every entry you have what they call a key and a value. It's sort of like those tag value pairs that I talked about in the data lecture a couple weeks back. So you can put whatever you want as the key and almost whatever you want as the key, and just about anything you want as the value. The rules for the keys are, first of all, they have to follow variable names, so they can't start with a number or something like that, and they can't be a number, I don't think. And they also have to be unique. You can't have a dictionary with several keys that are the same, because the key is what lets you look something up. And so you need to get a unique answer when you look up a particular key. So my mental concept, the metaphor or the example that I use is the amino acid code. So for the keys now are the DNA triplets, and the values are the amino acids they correspond to. So there can be several different keys that have the same value. Valine has several different codons, but for every codon, there's a unique amino acid that it produces. And every codon is only in the table once, right? You only have one lookup value for ACA. It always gives you the same unambiguous result. So that's a dictionary. So I give you an example, my dictionary. One of the ways, the most cumbersome and least efficient way to create a dictionary is to type it in. If you want to do that, it uses curly braces to define the dictionary. So now we have 3 different kinds of punctuation. We have normal parentheses, which define a list, square brackets, which define an index number in a list, and curly braces, which are used to define a dictionary. The items in the dictionary are defined or are separated by commas, and they're defined with a colon. You have a key, colon, value. In this particular dictionary, I've made both the keys and the values as strings. The keys are DNA triplets, and the values are alphabetic letters that correspond to amino acids. So this is a little snip of a codon table defined as a dictionary. So why are dictionaries important? Well, they're very useful as a lookup list. If you're going to frequently need to look something up, and then if you define it as a dictionary, the computer is able to keep in memory all the keys. And finding an element in the dictionary by asking it for the value assigned to this key is a one-cycle compute operation, very fast, as opposed to if you had that as a list and you asked it, it would have to look at every element in the list and ask, is this ATG, is this ATG, is this ATG, is this ATG? It would be much slower. If your list was a few billion long, it would be a lot slower, whereas it can still keep a few billion keys in random memory and jump directly to the one you're asking for. So, and it does that computationally. It's coded in efficient ways in machine language. So a hash, a dictionary, allows you to access a lot of data much more quickly. So it's a good way of indexing your data for efficient computation. So this is, again, like a big data concept. K-mer lists is another thing. I'm not, unfortunately, going to be able to teach you anything about K-mer lists in this part of the course, but if you stick around for more advanced bioinformatics, we'll use K-mer lists a lot. K-mers are like 3-letter words in a DNA sequence, or 8-letter words, or something like that, that allow us to, make computational ideas real in computing. So very fast random access lookup. The keys must be unique. Values can be just about anything. I mean, you could put a list as a value in a dictionary. You could put other more complex data types in there. As long as there's a unique key and it follows the rules that I just listed, it'll work. There's a function called zip that is an easier way to make a dictionary. So if you have 2 lists, you can say one of my lists is going to be the keys and the other list is going to be the values. I'm going to zip them together, and it knows that zip automatically creates a dictionary. Of course, you would want to say my dict equals zip of something in order for that to be saved as a variable that you can use later in your computing. This way, it just spews it on the screen, not super efficient. So I probably should have done it that way. It should be obvious that you need to have the same number of keys and values, or else zip won't work nicely. Probably won't work at all. Yeah?
So why is zip function not listing as a curve?
Yeah, I don't know. I think because it's a function. So all functions are defined as taking their parameters inside of regular parentheses. So it's not making a dictionary. It's a function that makes a dictionary, if you know what I mean. So that's the rule system that it operates under. It's a function that actually calls a bunch of other more complex commands that actually make the dictionary, but it hides it beneath the surface in a black box. Okay, an example of when a dictionary is really happy. Oh, I do have a K-mer example. Cool. So another useful application. For each item, check if it's in a dictionary. If it's not in the dictionary, add it to the dictionary. You can also count how many times it occurs at the same time. So this is saying how many dimers or how many unique dimers are present in this string. As is frequently the case, if you're going to do something inside of a loop and you want to preserve that data outside of the loop, you want to create the data element that's going to hold your result before you start the loop. So I'm creating here an empty dictionary called dimers. And inside of that dictionary, in the loop, I'm going to be writing all the possible dimers that I find in this string of DNA. So for x in range, length of DNA, again, x is going to just go through my string one letter at a time. Showed you that already. Create a new variable, di equals DNA of x to DNA of x plus 2. That little colon means a range. We did list slicing last week, right? So this is a slice of my list from x up to the next one. Up to the next one because it's x plus 2 index, and so it gives you the first two, not including the last number of your slice. You can check this. I checked it. It works. If di in dimers. So this is a cool little syntax here that is enabled in dictionaries. It's essentially a dictionary method in. So if di is already in dimers, if I already have a key in dimers that represents the two letters that I now have in di, then count 1. In other words, the value for that two-letter key is now increased by 1. So we have a key, and we increase it by 1. Initially, di won't be in dimers because dimers is empty. So we'll go to the second half. Else, dimers of di equals 1. So I've written into dimers a key value pair that is 2 letters, and we've seen those 2 letters one time. And then it just finishes the loop. So now it goes to the second dimer. It iterates up 1. And so we have a GA, and GA, after this loop is finished, we have in the list, we have GA colon 1 is our first dictionary element. And then we have AT. And is AT already in our list? No. So now we'll add to our list, after a comma, a second dictionary entry, AT of 1. And then we'll add a TC, a CC, a GG, etc. Eventually, we'll come to a dimer that we already have. Well, I think the first one that repeats would be TA. So when you get to this second TA, it looks up all the keys, and it sees that you already have a key for TA. So rather than adding a second one, which you're not allowed to do, you're only allowed to have one unique key, it says, oh, TA is already in here, so now I'm going to change the value of TA from 1 to 2. I'm going to add 1 to the value of the key for TA. So when I'm done with print dimers, it should tell me for all the dimers that are here and how many times each one occurs. That could actually be computationally interesting if you're an algorithm person or someone has asked you a simple question that could be answered with some kind of K-mer-based math. Like, are these two strings have a different frequency of GC dimers or that sort of thing? Yeah?
How long are dictionaries stored for? Is it just until you close out of Python?
Well, actually, typically you would create a dictionary inside of a program, and while that program is running, your dictionary exists.
So you have to make the new dictionary each time?
Pretty much, unless you have stored a set of key value pairs as a text file, and inside of your program you say read that and write that into a dictionary, right? But in general, all Python programs are like that. All the variables are created dynamically as the program runs. The data is usually stored as text files, which are read by the program. So you would probably want to have, say, a set of, a set of codon tables stored in a way that could very easily be turned into a dictionary as your program runs. I'm going to show you that in a sec because I thought it was a handy idea. But this check and add to dictionary is the solution to about 4 or 5 different Rosalind problems. So I got very fond of it. So here's a challenge, another assignment. Do or don't do or get help, just like before. This one, though, you could send to the assignments at Fenulab address as a bit of Python code and write the output as well and attach that in. So your result should be some code and a little sample of your output. So write a function that translates a DNA string into protein. And I'm actually letting you use whatever DNA sequences text you want. I should have given you a sample. Maybe I'll add a sample to the to this lecture. I'll add sample DNA tomorrow so that I know that your program works just very quickly, and I'll make it pretty small. So write a function that translates DNA into protein. In your function, use a dictionary of triplet codons as keys and amino acids as values. Begin translation at the first ATG. So you may need to use a find ATG as part of your code, or you could just go through every triplet moving forward by 1 base until you find an ATG yourself. Write a program that uses your translate function. So first you have a translate function, and then use your translate function to translate a file which you will receive as text. So you'll have to read that file in your program. The program should be flexible that it could read any file. So you take the file name as input that contains a single DNA sequence as text and write the output to another text file. So here's help to this program. I found this online. I didn't figure this out myself. Here's a very nice, efficient little piece of Python code that creates for you a dictionary of codons as keys and amino acids as values. So 2 statements. Codons is this list. Amino acids is this string. And then you create codon table with a zip function, dictionary, zip, codons, amino acids. Maybe I should have used this dictionary zip in the previous example. And here's the credit to Peter Collinridge, who wrote this code. So this will make your life easier. OK, a little philosophical side, and then we'll be done. When should you find and reuse code written by others, like this? And when should you write your own? So in bioinformatics, many of the problems you will encounter have been faced by other people. And a great deal of code has been written and shared in public repositories. Some of this code has been published and cited in the literature, and therefore is essentially validated. Someone else has looked at this code and found it to be good, true, workable, correct. Obviously, there's some code that's very complex and sophisticated and has been tried and true and tested and is, the best that the entire worldwide community is able to come up with. So you don't really want to rewrite BLAST unless you really have to. If you can't find the code to do exactly what you want to do, which happens, you're creative people, you have a new idea for analysis of your particular peculiar data that's maybe a new data type, or something needs to be done that hasn't been done by any other software, which essentially is the reason we're trying to teach you how to code. Should you adapt existing code or write your own? So there's challenges to figuring out someone else's code, really getting in there to the point where you can make changes and get a useful result rather than just breaking it. New code that uses code from other people that has dependencies is pretty fragile, because those other codes will update over time, and now your code may or may not work with a different version of other pieces that it depends on. There's also challenges if you write your own code to validate it. So essentially in publishing, you're now going to have to prove not only that your scientific results are correct, but also that your data analysis methods are correct, because you're using novel methods. There's also value in building your own repository of code elements that have been tried and tested by you, that work and fit together in a way that makes sense to you. And that sort of makes you the guru of your own little code empire. And that's how all of the useful code projects that I'll introduce you to got started. Somebody didn't find the tools that they wanted, and so they started building those tools and saving them and building tools that link together in logical ways until you end up with something like BioPython or Bed Tools or SAM Tools or many of the other software environments that I will mention in bioinformatics in the future. Okay, 2 more slides. This is not teaching you this stuff, it's a heads up. So I mentioned NumPy, which is built into Anaconda, but is a pain in the butt to install yourself if you've installed Python source code and not a distribution that has an installer. Has some basic statistic functions that work on arrays. I introduced arrays last week. Arrays are like lists, but they have defined numerical elements. And you can very easily get multidimensional arrays, which are like lists of numerical values. So we have things like square root, squares, mean, median, standard deviation, which are built into NumPy. So you would sort of import NumPy as NP and do these operations. These operations are not built into regular Python. Mean, median, standard deviation are statistical operations that you get from one of these additional sort of computational or scientific packages, or numerical in this case. NumPy has a bunch more advanced mathematical stuff: linear algebra, trigonometry, logarithms, permutations. It also has some built-in distributions that you're going to start using in a couple weeks. The normal distribution, the Poisson distribution, etc. So you'll be using this a lot. This is just a heads up that if you want to do this sort of stuff, this is what you'll do. You'll call Python, and then you'll import NumPy, and then you'll have access to these additional data crunching tools. Right? It's a toolkit. All right, this is really just a heads up. SciPy is an extension of NumPy that provides more complex mathematics, statistical, and scientific data analysis functions. And then this is just a fun thing for you at the very end of the lecture. Okay, so we did this: flow control, operators, for loops, recursion, reading and writing files, creating your own custom functions, and an introduction to dictionaries. I gave you 2 assignments, right? Fibonacci and translate function. And next lecture is going to be BioPython. Yeah.
For that translate function, the DNA that you give us, once we find that whatever was ATG or the start sequence, can we assume that the code will end on
No. So it should be, you should be able to handle that, right?
So if it doesn't end on a triplicate, what would it?
Well, you should probably not try and translate it if it's less than 3 letters long. Well, a simple way to do that would be with this in function. So if the value is in the dictionary, then translate it. And if it's not, you can just do nothing, or you could say end of code or something like that, end of input. Probably doing nothing is going to be the easiest response. In fact, even if you leave that out, if you just do a lookup of the key in the table, if the lookup fails, it'll handle that in some sensible way.
You can also just use the try operator. You just do try, and then it's again with dots, also with the colon, basically, and then everything that comes past this sort of try statement, Python will try to parse through it, but if it returns an error, it just stops.
So that's another function. Yeah, so that's making use of another function that does essentially the same thing.
But most of the time, you actually want to get the error because that means there's something wrong.
Mm-hmm. Yeah. Now, in real proteins, maybe you get a stop codon, but lots of times not. Lots and lots of times not, because things just end, right? So your translator probably shouldn't be dependent on finding a stop codon. Yeah, but figuring this stuff out, that's actually the point. All right, so those of you who didn't finish the Rosalind or want help with these 2 new assignments, grab a drink and go over to Translational Research 7th floor. The tutors are there. If you're good, then you're good, and we'll see you on Tuesday.
Where's the sign-up sheet?
Oh, the sign-up sheet, yeah. And anybody who didn't get the sign-up sheet, do it. And if you didn't hear me, if you finish the 6 Python Village Rosalind programs, put a little R after your name or after your email address on the list so I can say, yes, you finished, because I don't really want 50 emails with screenshots. That seems boring.